Hello there. During this session I'm going to be explaining how we're able to capture digital images today. The focus of this session, I'm going to start off by talking about what capacitance is, and then I'm going to be explaining how a CCD works. And we'll go into more details of what this all means in a moment. First of all, I'm going to talk about this thing called capacitance. So capacitance is typified by a parallel plate arrangement and is defined in terms of charge storage. So let's go through this slowly. Is typified by a parallel plate arrangement. A capacitor, and here's an example, normally has set up two parallel plates. Okay. We want these parallel plates to have as much area as possible, so we often find if you opened up a capacitor, and here's a capacitor image which has been opened up, you'll find that there's two plates wrapped around as much as possible, so therefore you can have the maximum area of two parallel plates. Defined in terms of charge storage. Okay, so the purpose of these parallel plates is to store as much charge as possible. It's a charge storer. So capacitance equals the charge stored divided by the voltage applied to the plates. Okay, and what we're looking for is we're looking for something to have be able to charge as much or store as much charge as possible with the smallest voltage possible, and therefore to have the most capacitance. Okay, so crucially, it's a device for storing charge. How it would work in a circuit would be if you introduce a capacitor, and the symbol there is the two parallel lines we have to a basic circuit. What happens is initially there'll be a large current, and the potential across the capacitor would be zero, and then it would start to charge. Okay, so it would charge up, and therefore the potential across the capacitor will start to increase, and it will start to increase up to the point when the voltage of the capacitor is equal to the voltage being provided, and that's when it's fully charged. Okay, so it will take up a certain amount of time to become fully charged for the situation, and then you have a stored charge facility which you can use and release as and when is required. So here's a question about capacitor. Looking at the large blue capacitor, how much charge can it store at maximum voltage? So we look at the information there. Well, 50 volts is the maximum voltage, and we've got 1000 microfarads. So therefore, do the calculation, it can store 0.05 coulombs of charge. So that's some background into what a capacitor is. I'm now going to switch, and I'm going to start talking about these things called CCDs, and there's a reason why I put capacitors first. Okay, so what is a CCD? Well, a CCD is a bit like a capacitor. It's something which allows us to store charge, and it works in a similar way, and we might have to use the mathematics of a capacitor to help explain some of the ideas of what a CCD is. Now, a CCD stands for a charged coupled device, and what it really is a silicon plate which allows us to convert an analog signal of light images into a digital signal. So it's an analog to digital converter of some sort, but for images. So how it works is, first of all, we have set up our CCD, and what it's done is that it can be placed into a camera or a camera-like object, and on the focal plane of the camera we place this silicon chip. Okay. Now what happens, pixels, and the pixels are each of the little sections on this silicon chip are each able to convert light intensity into electrical charge, okay, which is stored on the pixel. So there's charge being stored on the pixel, very similar to the behavior of a capacitor, and that means that we can work out what the image is by processing this information. Okay, so let's look at this in a little bit more detail. How it really works is that when light falls onto the silicon, remember the photoelectric effect? So what happens here is the photon strikes the silicon. It's very likely to displace an electron from the thin layer of silicon, and therefore the displaced electron, as soon as it's displaced, is collected in the pixel. So that means for every bit of light which falls onto the silicon, then a charge, an electron's charge, is reproduced and captured at that point in time. So therefore, the more photons which strike the silicon, the more electrons which are produced. Okay, so the greater the buildup of charge. Let's see how this works. Okay, on a bigger picture. Okay, so what we've got a whole sheet of image being projected onto. So there's different light in different locations. So what do we do about that? So what happens is at the end of the exposure, so expended amount of time, the charge is then transferred. Okay, so this is done pixel by pixel at a time. So every single pixel there, we'll look at how much light has fallen on that point, and from there we're able to create a digital image. So the electrical connections are made to the outside world via a bunch of bond pads and thin gold wires positioned around the outside. Okay, so that's how we access the information. We take away the charge. I'm going to use an analogy to show how this works. So there's a common analogy for the analog to digital converter in a CCD. I'm going to imagine a number of buckets, which are pixels, distributed across a field. This is the focal plane of a camera in a square array. The buckets are placed on top of a series of parallel conveyor belts and collect rainfall, the photons, as they fall from the field. The conveyor belts are initially stationary while the rain slowly fills the buckets. So this is the exposure time. Okay. So depending on how long with the exposure, more rain is collected. So that's like more photons being collected. Once that's over, then the camera shuts, and then we need to process this information which has been collected. So what happens is the conveyor belts start turning and transferring buckets of rain one by one into a measuring cylinder. And this is the electronic amplifier at the corner of the field, at the corner of the CCD. So what we're doing for every single pixel, we're finding out exactly how much charge was captured. And remember, that charge relates to how many photons fell on that one point. Let me take you through some steps. So here we have the exposure is finished, and the buckets now contain some samples of rain. So what I'm going to do is I'm going to slowly bring those conveyor belts and bring the rain across onto a vertical conveyor, and it tips the buckets onto the horizontal conveyor. Okay. Then from there I'm able to stop and wait, and each bucket will be going to a measuring device, the measuring cylinder. So I know exactly how much charge is from every single one of those pixels, and that tells me how many photons fell on that pixel. I go through the process. Let's say the number was 8. I carry on this process, building up information. Again, carry on the process, building up information. Building up information. And building up information. Till eventually I recognize that I have a breakdown of exactly how many photons fell on every single pixel. Now, this gives me a series of values, and those values I can now use and read out because I can convert them into a digital signal, okay, which is really, really, really useful. In reality, okay, we don't have integers of raindrops, okay, we have just the potential difference measuring across each pixel. So what we're able to do is we're able to measure the potential difference, and rather than raindrops, obviously we're talking about volts, which we can be read. So we have a series of values here. Okay. Now our snag is that, let's say we have these measurements up to 8 volts, is that if we have a 3-bit analog to digital converter, the amount of numbers we have is only going to be 7 plus 0 is 8 digits. So 4.1 and 7.5 and 1.6 are all going to be converted into one of the 8 numbers I have if I have a 3-bit analog to digital converter. So what I've got here is I've got all this data, and let's say the maximum output voltage for pixel after amplification is 8 volts. Okay. Now each one of these voltages is converted into a rounded number and then into a digital output. So that means that all the data I'm collecting for each one of these pixels is then converted into a digital output, which is obviously shown in binary in zeros and ones. So now I've got details about how every single pixel, how much light fell on it in a digital format, which is really, really useful, because then it can be converted by a computer to reproduce that image.